So, as I said, last lecture of the year. Super exciting. All right, so a couple of things that you're going to have to do. We're going to do what are called probability distributions. And I have gathered data for you and listed it here in some form. So this particular one, the Student Council recently surveyed 500 students to determine what activities are most popular for Spirit Week. So how many students were surveyed? 500 students. So that's the total number of students that were asked about their choices. So this is total. If you look at the number of votes for dance, rally, costume contest, class competition, what do you notice about the total number of votes?
There are more than 500.
There are more than 500. So what can you conclude about the survey?
That's more than 500 people.
Cameron? Each person had more than one vote, so they could have voted for more than one thing, not just one item. So you might say, oh, I like the dance, the rally, and the costume contest. Who cares about classroom competition? So maybe somebody voted for 3 things. So you might want to note here to the side that each student selected more than one item. Or had the opportunity to select more than one item. Yes?
Would say that one of them could have only voted for one thing and one voted for all 4?
Correct. Yep.
Isn't that a bit
No, because they're getting a survey on, out of those 500 kids, what was most popular out of those activities. So if every activity was equally popular, then they would continue to, do those activities. If one activity is quite obviously not as popular as the others, so what appears to be the lowest liked activity? The class competition. So maybe there's no point in continuing with that particular, because maybe they want to try something new. So the purpose of the survey is to see what y'all liked, what you didn't like. So it's a decent way to survey. So the first question says, based on the chart, what is the probability that a student from this group voted for a dance? So from this group. So we want to know the probability. So remember, how do we find probability? Favorable over total, right? So how many students voted favorably for the dance?
310.
310 out of how many total students voting? 500. Now, each of those 500 students, you notice that none of the votes were more than 500. In other words, they're not going to vote for dance twice. It's not like American Idol, right? You can keep voting for the same person over and over again. So they can only vote for each one at least once, or no more than once. So if for some reason one of these was more than 500, we'd be suspect as to why. And so as you look at this, you can actually say, okay, most kids like the rally and the costume contest, right? So we're going to reduce this. The zeros cancel out, and you actually have a fraction probability of 31/50ths. So you can have that as your answer. Or oftentimes it's more valuable to look at the decimal probability, because then it tells us what the percent is. So if you divide that on your calculator, it would be approximately 62%, because it'd be 0.62. The squiggle, you could. Yep, but it won't always be exactly 50 in the bottom. If I just ask for the probability, you can give me either this or this. Either one's acceptable. This is the more accurate one. Yeah. And if I wanted the percent, I'd say write it in the percent. All right, so then the second question says, how many of the 1,400 students who did not take the survey? So the whole point of doing this is I can extrapolate, which means that I can take this percent and say, okay, I surveyed 500 students and then 1,400 I didn't. So how many students total are there? What's 1,400 plus 500? So this school must have about 1,900 students. So I can say that, based upon this, just surveying 500 students out of that population, 62% of them liked the dance. So I can kind of assume that 62% of any student would like the dance. So if I've got students who did not take the survey and I want to figure out how many of those wouldn't like the dance, I'm going to take my 1,400 and I'm going to go ahead and multiply that to either one of these 2%. If I were you, I would multiply it by the accurate one, which is 31/50ths. So there's the ones that didn't take the survey. This is the percent of the ones who did take the survey who liked the dance. So I'm going to put the 1,400 over 1, and I can start to cross cancel. This 0 cancels with that, and 5 cancels into 140 28 times. And so all I have left over is to multiply 28 times 31. And that gives you 868 students. So if I were to plan a dance, I would assume that 310 students plus 868 students might be willing to attend a dance. Would that kind of give me an idea of how to prepare for that dance? Yes or no? Because I'd need to buy certain things for the dance, whether it's to get the DJ, food, whatever it might be. Things that you're giving away to dance. I kind of need to know how many students are coming. Because otherwise y'all just show up and we don't know if it's going to be 2 of you or 1,500. Alright, so then let's look at questions 3 through 4. So this one's a little different. It says a survey asked homeowners how many televisions they have in their home. The results are shown in the table. So it says number of televisions, 1, 2, 3, or 4 or more, and then number of households. Let's see, this is going to be embarrassing, but in my household I have 1. Okay, technically I have some in a closet that aren't plugged in, so I won't count those. So 1, 2, 3, 4, 5. I actually have 5 in my house that are plugged in, plus 3 in the closet that don't work. So technically I have 8. Because we haven't ever run out of TV. I mean, I literally have TVs from 1987. Because it still works, I just don't, it's big and bulky. Well, I have a TV in my bathroom, so I can watch TV while getting ready. I have a TV in my kitchen, so that I can watch TV when my husband's watching his boring TV. So and then my kids each have a TV in their room. Because she doesn't watch TV. All right. Neither here nor there. How many of you have 4 or more TVs in your household? Just raise your hand. Thank you very much. I am not out of the ordinary. How many of you have 0 TVs in your house?
Oh my God.
Now, do you have? Wait a minute. You have a TV at your dad's house, don't you? Okay, so that counts. She has at least 1 TV. All right. So, shh. There are some people that actually don't watch TV. It's shocking but true.
Have a TV, but I don't watch it.
You'd be amazed at what things you find to do when you're not sitting on your butt watching TV. Now, typically when I'm watching TV, I'm doing something else. I don't typically sit and watch TV for the sake of watching TV. But that's just me. All right, so back to the question at hand. Shh, look at what's going on. It says, TJ, it says, find the probability that a randomly chosen homeowner has 1 television in their home. Did each household make more than 1 choice, like the previous example? No. So as a household, you're going to choose one of those categories. They didn't give 0 as a choice because most people don't have 0 TVs. So one of the things that we're going to need to do is find the total number of households that were surveyed. Do I know that just by looking at the table? No. So I have to add up 42, 38, 25, and 11. And if I add those up, I get 116 for a total. So, find the probability that a randomly chosen homeowner has 1 television in their home. How many households had 1 television? 42 out of how many households? 116. Can that be reduced? Yeah. What numbers go into 42? At least 2, right? So divide this in half, you get 21. Divide 116 in half, you get 58. What are the only numbers that go into 21? 3 and 7. What's 5 plus 8? 13, does 13, is that divisible by 3?
No.
No. Does 7 go into 58?
No.
No. So that's fully reduced. If you wanted the decimal equivalent, see if you divide this out, you would get 0.36, which is 36%. So almost, or a little bit more than a third of the households have just one television. And that's the majority on this survey. In this classroom, it was a little different, wasn't it? Just a little different. All right, so then it says, find the probability that a randomly chosen homeowner has more than 2 televisions in their home. More than 2 televisions. Do I count category 1? Do I count this category? Yes or no?
No.
No. Do I count this category here?
No.
Because 2 is not more than 2, right? So I've got to count the category of 3 and 4 or more. So I have to add the 25 and the 11 together and put that over the 116. Don't I? Plus 25 plus 11? 36 out of 116. So divide 36 by 2. You get 18 out of 58. Can that be reduced more? Yep, divide it by 2 again. 9 out of 29. 29 is prime, right? So we have 9 and 29, which it'd be nice to compare that to percent. So if you divide that, you get 0.31, which is 31%. So these two together, 3 or actually more than 2 televisions, almost equivalent, slightly under the number of households that have 1. All right, so then flip to the back, and we're going to do 9 through 11. So 9 through 11 and 12 through 14 are the same, and let me just point out, by the way, that 5 through 6 is the same as which one? Five through 6, a teacher recently gave her 50 algebra students a 5-question quiz. The table shows the number of students who answered each question correctly. She's got 50 algebra students. What do you notice about here? So which one of these two is 5 through 6 similar to? It's similar to 1 through 2, right? So this one's like 1 through 2. Then flip it to the back. Look at 7 through 8. Notice that this one says the owner of a barber shop asked customers how many haircuts they received in a 3-month period. Results are shown in the table. Which one is this one similar to? The television example, right? So I've done one of each one of those so far, correct? So you've got each one of those left to do. These two are just alike also. So that's why I'm doing 9 through 11, and then you'll do the other 3 on your own. So this one says the table shows the probability distribution. So this is something new to you. What's a probability distribution? Of the number of telephones per student's household at Wilson High. So X represents the number of telephones. So in a household. So you have the 1 telephone, 2, 3, 4, 5 or more in a household. Shall we count telephones now?
So.
Well, I only count my landline as 1 phone, even though it has several that go in each room. It's technically only 1 phone. It's attached to several. How many of you, everybody in your family has a phone? Everybody in your family has a phone. Why is that? Because phones are so much more affordable than they ever used to be. It used to be outrageously expensive to even have a cell phone. And it used to be for every telephone line that you had to pay for that line. Well, then came the age of digital phones instead of a rotary dial phone. See, I came from the era of where you go, you dial the phone, it goes, you dial another number, it goes, I mean, it took forever to dial a phone number. Now you just press a button and it dials the whole thing. Back in the old age, I used to have to trudge to school in the snow, uphill and downhill.
He says that all the time.
That's because it's a joke. All right, so obviously most families in this day and age are probably here, so this survey is a little old, isn't it? Okay, but neither here nor there. That means that if you add all these up, by the way, you have to determine, the first question says, show that the data is a valid probability distribution. the first thing that you have to determine is, do these add up to more than 0? And it seems kind of a ridiculous question, but it should add up to 1. They should. And so the very first thing you're going to do is ask yourself and determine, are all probabilities greater than 0? So each one of them are greater than 0, right? And the second thing is that they should add up to 1. Because we are surveying 100% of a population, they better add up to 1. So let's add them together. So I've got 0.1 plus 0.16 plus 0.32 plus 0.39 plus 0.10. If we add these up, 1 and 6 is 7, 7 and 4 is 11, 11 and 9 is 20, so that's a 0, carry the 2, so I have a 2 carried, so 2, 3, plus 3 is 6, plus 3 is 9, plus 1 is 10. We only had 2 decimal places. Oh, you can't see. Why don't you say something earlier? There you go. So don't they all add up to 1? And they should. If they don't, something's wrong. All right, so that's how you're going to validate the distribution. There's 2 parts to it. Number 1, all probabilities, each of these are greater than 0, which they are. And then the second part is that they all must add up to 1. So then we can go on and answer some more questions. So then the next question says, pull that down. If a student is chosen at random, what is the probability that there are more than 3 telephones in the student's home? Does that include 3 telephones? Does more than 3 include 3? No. So we want to add together just these 2, right? So we're going to add together the 0.39 plus, and these are probabilities, plus 0.10. So 39% plus 10% equals what? 0.49 or 49%, right? Almost half of the households have more than 3 phones, 4 or more phones. So you just have to figure out what sections of that you have to add up. It's not that hard. Then you have to make a probability histogram. What do we know about histograms? Yeah, there's no spaces, and they tend to have intervals, but this is slightly different. So what you're going to do is you're going to put your probability on your vertical scale. So this is going to be your probability. And our probability ranges, the smallest probability is 1, and the highest, use a tissue, is 0.39. So we need to go from 0 to 40, essentially. So I'm going to go by tens on here. So this is going to be 10%, 20%, 30%, and 40%, give or take. It's a little fuzzy. Nope, that's as good as it gets. I think. Let's see what that does. Nope, that's what. Oh, see, that's slightly better. You probably think I'm crazy. I know you do. I view the world as fuzzy all the time. All right, so then I have how many things up here? It's true. Don't I have 1, 2, 3, 4, 5 things here? So we're gonna have 5 bars. Each of these represents a bar. So I'm gonna split my bar into even 1, 2, 3, 4, and 5, because I want them all to be the same width. So this is going to represent 1 telephone, 2, 3, 4, and then 5 plus. And you need to label this as number telephones per household. So you have to label your axes, and then we should have a title. What's a good title for this?
Telephone.
Well, look at what we surveyed here. Number of telephones per student's household at Wilson High. So you might want to write up here, number of telephones per household at Wilson High. The more descriptive you are, the better off we are. Alright, so then for one telephone, how high is our bar? It's really low, isn't it? If this is 10%, then 1 might be right there. So use a ruler. So it's going to be just a sliver. Just a sliver. And it might have gone just a little big of a sliver, but that's all right. And then for 2, we want to go 16. So 16 would be about halfway, right? Give or take. And then for 3, we want 34. So again, that's almost halfway again. And then 4 telephones is 39, so it's really almost a 40. And then for 5 telephones, that's 10%. And that's it. So you'll do the same kind of thing here. And so now you can visually see that the majority of homes have 3 or 4 televisions in them, right? Very few homes have just 1, and very few homes have 5 or more telephones per household. Now if you include cell phones, in my house I have 4 landlines attached to 1 landline plus 4 cell phones. 8. All right, any other questions? All right.